Hey everyone, and welcome to a deep dive into the quantum realm. I'm excited to explore some fascinating physics concepts with you today. We've got some intriguing notes to guide us. We're going to try to unravel the mysteries of modern physics. Things like the photoelectric effect, wave-particle duality, even how atoms reveal their secrets through something called atomic spectra.
It really is a fascinating area to explore.
Yeah.
We're going to be going beyond the familiar laws of classical physics that govern our everyday world and venturing into a realm where light and matter behave in ways that can be a bit counterintuitive.
It's kind of like we've been using the wrong instruction manual for the universe all along.
Haha, right.
But let's start with something that sounds pretty straightforward. The photoelectric effect.
Okay.
What is it, and why did it cause such a stir in the physics world?
So imagine you're shining a beam of light onto a metal surface.
Okay.
What would you expect to happen?
I guess I would just expect it to heat up.
Yeah, that's what you might think, but under the right conditions, something way more interesting happens. The metal starts emitting electrons. It's like the light is knocking these tiny particles loose.
Okay, so light is interacting with matter, and that releases electrons.
Right.
Why was this such a puzzle for physicists?
Well, because classical physics treated light as a wave,
Right.
and it couldn't really explain this.
Okay.
According to that wave theory, the energy that light carries should just depend on its intensity. Basically how bright it is.
So you would think brighter light would give the electrons more energy and you'd get more electrons flying off.
Exactly, but the problem was experiments showed something totally different.
Ah.
The energy of those emitted electrons didn't depend on the brightness of the light at all.
So what did it depend on?
It was directly linked to the frequency of the light, its color.
So is it like the electrons are being picky and only respond to certain colors?
Yeah, you could think of it that way, like shine a dim blue light and those electrons might just fly off with a lot of energy,
Okay.
but then shine a really bright red light and nothing happens.
Interesting. So it's not the amount of light, but the type of light that matters.
Yeah, and that's where Einstein comes in and really changed how we understand light.
Hmm.
In 1905, he proposed that light isn't just a wave, it also acts as if it's made up of these tiny packets of energy called photons.
Aha, photons, those little bundles of light energy we hear so much about. So how did that explain the photoelectric effect?
Okay, so think of it this way. Each photon has a certain amount of energy, and that energy is directly proportional to its frequency.
Okay.
A blue photon, with its higher frequency, packs a bigger energy punch than a red photon.
Got it.
And when that photon hits the metal, it can transfer all of its energy to an electron. If that energy is high enough to overcome what we call the work function, basically the energy barrier holding the electron in the metal, then boom, the electron gets ejected.
So it's like each photon needs the right key to unlock that electron from the metal.
Yeah, great analogy, and it gets even more interesting. Einstein's photoelectric equation actually describes this whole interaction. It basically tells us that the energy of the photon, and remember that's determined by its frequency, has to be equal to the work function of the metal plus the kinetic energy of that ejected electron. The energy it has as it flies away.
So the equation is accounting for all the energy in this little subatomic interaction. It's really amazing how this seemingly simple phenomenon caused such a huge shift in our understanding of light.
It is.
But what are the real-world implications of this photoelectric effect?
Oh, the implications are huge. Like, think about solar panels.
Okay.
They convert sunlight into electricity, right?
Right.
That's thanks to the photoelectric effect. Light hits the solar cell, knocks electrons loose, and then those electrons flow as a current.
Wow, so we're harnessing the power of the sun all thanks to Einstein's insights into the nature of light. What other applications are there?
Well, digital cameras rely on it to capture images. Light sensors convert those incoming photons into electrical signals, which then get processed to create that digital image. And those automatic doors that open when you walk up to them, those use photoelectric sensors too.
Oh, wow. I didn't realize that.
Yeah.
It's incredible how a phenomenon that was so baffling to physicists over 100 years ago is now just part of our daily lives.
It really is.
But before we get too carried away with the photoelectric effect, we've got another mind-bending concept to tackle. Wave-particle duality. This one involves electrons acting like, well, I hear it involves them acting like surfers.
You're not too far off.
Good.
But before we dive into those electron waves, let's take a step back. Classical physics, with its neat separation of waves and particles, seemed to work fine for describing the everyday world.
Yeah, the things we can see and touch.
Exactly. But as scientists delved into the realm of atoms and those subatomic particles, they found things that classical physics just couldn't explain.
It's like they found a whole new set of rules at that incredibly small scale.
Yes. And one of the most surprising discoveries was that particles, like electrons, could actually behave like waves.
Hold on, those tiny electrons that make up atoms, those are acting like waves.
It does seem counterintuitive, right? But this idea, it's called wave-particle duality. It basically states that every particle of matter has a wave associated with it. And the wavelength of this matter wave is related to the particle's momentum.
Okay, so momentum is basically how much oomph a moving object has, right?
Mm-hmm.
So a faster electron with more momentum would have a shorter wavelength.
Exactly. It's like the electron is riding its own wave, and the faster it goes, the more compressed that wave gets. Imagine like a speedboat on a lake. It creates those short, choppy waves. Now picture a barge just slowly moving along. That creates long, gentle swells.
I can picture that. So faster electron, shorter choppy waves, slower electron, longer gentle waves.
Right.
But this whole idea that matter can behave like waves is so bizarre. Was it accepted right away?
Not really. It was quite a radical idea. A lot of physicists were skeptical at first, but within a few years, there was experimental evidence confirming the wave nature of electrons.
What kind of experiments were those?
Well, one of the most famous ones is called the Davison-Germer experiment.
Okay.
They took a beam of electrons and fired it at a nickel crystal. And what they saw was a diffraction pattern.
A diffraction pattern.
Yeah, basically a pattern of bright and dark spots. The thing is, you could only explain that pattern if the electrons were behaving like waves.
So those tiny particles were diffracting like light waves bending around an obstacle.
Precisely.
Yeah.
And those experiments, they really revolutionized our understanding of what matter actually is.
It's amazing.
Hmm.
But this wave-particle duality, what does it really mean for us? Why should we care that electrons can act like waves?
Well, it really gets to the heart of why quantum mechanics is so mind-blowing. It tells us that at that really small scale, the difference between particles and waves gets blurry. Electrons, protons, neutrons, they can all act like both particles and waves. And this duality really changes how we have to think about the structure of atoms and how they interact with light.
So it's not just some theoretical idea.
Hmm.
It actually affects how the universe works. And speaking of atoms, our notes mention something called atomic spectra.
Right.
What are they and how do they fit into this quantum picture?
So atomic spectra, they're like fingerprints for different elements. They show us the unique energy levels that electrons can have within an atom.
Okay.
So when you heat an atom up or excite it with some energy, its electrons can jump to higher energy levels, but those excited states, they're not stable.
Yeah, they want to go back down.
Exactly. The electrons quickly drop back down to lower energy levels, and when they do that, they release energy as light. And the amazing thing is, the light emitted by each element isn't random. It consists of very specific wavelengths, which create a unique pattern of bright lines called a spectrum.
So each element has its own signature spectrum, like a barcode that identifies it.
Exactly. And by studying these spectral lines, we can learn so much about the structure of atoms and the energy levels within them.
It's incredible how shining light through a gas or just heating something up can reveal so much about the hidden world of atoms.
Yeah, it really is.
But I think we're going to have to pause here for a moment and let our listeners process everything we've covered so far.
Sounds good.
We've gone from the photoelectric effect to the wave nature of matter, and even gotten a glimpse into how atoms sing their unique songs. But there's more to come. Join us for the next part of our deep dive, where we'll go even deeper into the quantum world and explore how these concepts have shaped our understanding of the universe. Welcome back to our quantum adventure. Before the break, we were talking about how atoms sing their own unique songs through those spectral lines. But how do these spectral fingerprints actually connect to those quantized energy levels we've been discussing?
Okay, so let's picture those electron energy levels again, like rungs on a ladder inside the atom.
Okay.
When an electron absorbs some energy, it can jump up to a higher rung, but it can't just hang out anywhere in between.
Right.
Those energy levels are very specific, discrete, just like notes on a musical scale.
So the electron can only play certain notes on this atomic ladder, and each note is a different energy level.
Exactly. And when that electron decides it doesn't want to be in that excited state anymore, it jumps back down to a lower energy level. And when it does that, it releases that extra energy as a photon, a little packet of light.
So the energy of the photon determines the color of light we see. That's how we get those distinct spectral lines.
Precisely. The energy difference between those two energy levels determines the energy and thus the wavelength of the emitted photon. Since those energy levels are quantized, meaning they can only take on specific values, the emitted photons can only have certain specific energies.
So it's not just a random mix of colors, it's a precise set of wavelength that match those energy transitions in the atom.
Right. And to keep things organized, these spectral lines are actually grouped into different series, each named after the scientists who discovered them.
Okay.
You mentioned the Lyman series and the Balmer series earlier. The Lyman series corresponds to transitions down to what we call the ground state. That's the lowest energy level, where the electron is most stable. And these spectral lines are in the ultraviolet part of the spectrum, which we can't see with our eyes.
So those are like the high energy transitions where the electron is taking a big leap down the energy ladder.
Exactly.
What about the Balmer series? That's the one we can actually see, right?
Yeah, so the Balmer series involves transitions to the next energy level up from that ground state, and these lines fall in the visible region, giving us those vibrant colors we see from things like hydrogen and neon.
So depending on which rung of the ladder the electron jumps down to, we get different series of spectral lines at different wavelengths. It's like the atom is playing a different tune depending on how excited its electrons are.
That's a really good way to think about it. And by studying these spectral lines, we can actually map out those energy levels of an atom, understand its structure, and even identify unknown elements.
It's amazing how shining light through a gas or heating up a substance can tell us so much about the world of atoms.
It really is.
But let's move on to another type of light that's revolutionized science and medicine.
Yeah.
X-rays. We all know they can see through our bodies, but how are these powerful rays produced?
So X-rays, like visible light, are a form of electromagnetic radiation, but they have much shorter wavelengths, which means they carry a lot more energy.
Okay.
They're produced when high-speed electrons are suddenly stopped, usually by hitting a metal target.
So it's like slamming the brakes on a speeding electron, and that sudden deceleration generates those X-rays.
That's a good way to visualize it. The kinetic energy of that electron, the energy of motion it carries, is converted into X-rays when it hits that target. And just like with atomic spectra, X-rays can tell us a lot about the structure of matter.
Right, and I remember from our notes that there are two types of X-ray spectra, continuous and characteristic. What's the difference?
So the continuous spectrum, that's a smooth spread of wavelengths like a rainbow. It's caused by the general deceleration of the electrons as they hit that target. It's sort of like a broad brushstroke of X-ray energies. But then you have the characteristic spectrum.
Okay.
That one consists of sharp peaks at very specific wavelengths that are superimposed on that continuous background. These peaks are actually unique to whatever material the target is made of, which is why we call it characteristic.
So it's like each element has its own X-ray fingerprint, just like it has its unique set of spectral lines.
Exactly. And these characteristic X-rays, they actually come from a really interesting process that involves the inner electrons of those target atoms.
So what's happening at the atomic level to create these X-ray fingerprints?
When those high-speed electrons crash into the target, they can sometimes knock out an electron from one of the inner shells of an atom in that target material. Remember those energy levels we talked about, like rungs on a ladder? Well, these inner shell electrons are way down near the bottom of the ladder in very stable, low-energy states.
So it takes a lot of energy to dislodge one of those inner electrons.
A lot, and that's where those incoming high-speed electrons come into play. They have enough energy to actually knock out one of those inner electrons, leaving a vacancy, an empty spot in that inner shell.
I bet nature doesn't like those empty spots in its atoms.
You're right. An electron from a higher energy level, further up the ladder, will then quickly jump down to fill that vacancy. And just like with those visible light spectra we talked about, this transition releases energy in the form of a photon.
But this time it's an X-ray photon because the energy difference between those inner shells is much greater.
Exactly. That energy released is high enough to produce an X-ray photon. And since the energy levels within an atom are quantized, those X-rays have very specific energies, which leads to those characteristic peaks we see in the spectrum.
So by analyzing these X-rays, we can learn about the arrangement of electrons in the inner shells of atoms. It's like those X-rays are giving us a peek deep inside matter itself.
That's a great way to put it. And just like with atomic spectra, this X-ray spectroscopy has become this incredibly powerful tool for identifying elements and studying the structure of atoms.
This is all so mind-blowing.
Yeah.
But I think we need to take another little break here to let our listeners catch their breath.
Okay.
We've covered a lot, from the photoelectric effect to wave-particle duality, atomic spectra, and now X-rays. Join us for the final part of our deep dive, where we'll tie all these concepts together and look at their impact on our understanding of the universe and the technology we use every day.
Welcome back to our final exploration of the quantum world. It's been quite a journey. From those rebellious electrons escaping metal surfaces thanks to the photoelectric effect, to particles behaving like waves, and even atoms singing their own unique songs through spectral fingerprints.
It really has. And we even talked about how X-rays, which are powerful enough to see inside our bodies, come from suddenly stopping those high-speed electrons.
Right. But with all this talk about quantum phenomena, it's easy to get lost in the abstract. How does all this actually impact our lives? Well, that's a great question. It's easy to get caught up in the concepts, but the impact on the world is huge. You mentioned medical imaging before.
Right.
How have X-rays revolutionized healthcare? I mean, think about it. Before X-rays, doctors had very few ways to see inside the body without doing surgery.
Yeah, that makes sense.
X-rays let us see bones, detect fractures, diagnose so many conditions without being invasive. It was a huge change for medicine.
So X-rays, those things created by slamming electrons into metal, literally gave us a window into the human body.
Exactly.
It's amazing. But X-rays are just one example of medical imaging that relies on quantum mechanics.
Yeah, absolutely. There's MRI, magnetic resonance imaging.
Right.
It uses quantum properties of atomic nuclei to create detailed images of soft tissues, organs, even the brain. And then there's PET scans, positron emission tomography, which uses radioactive isotopes and their quantum behavior to track metabolic activity. It helps us diagnose and monitor conditions like cancer.
So many essential tools in healthcare rely on our understanding of the quantum world. What about other areas? Where else do we see this impact?
Oh, it's everywhere, like electronics. Modern electronics are completely based on how electrons behave in materials, and that's all governed by quantum mechanics. Transistors, those tiny things that make up computers and smartphones, they work because of something called electron tunneling.
Electron tunneling.
Yeah, it's a quantum phenomenon where electrons can pass through barriers that classical physics says they shouldn't be able to.
Wow. So our ability to communicate, get information, even just have fun, it all comes down to those strange rules of the quantum world.
That's right. Our modern world is built on those quantum foundations. And the more we understand, the more potential we have for future innovations. Quantum computing, for example, has the potential to revolutionize fields like materials science, drug discovery, and AI by using quantum superposition and entanglement.
Quantum computing, that sounds pretty futuristic.
It does, but it's a fast-growing field, and it could help us solve problems that are impossible for our regular computers to handle. And who knows what other breakthroughs are waiting for us as we learn more about the quantum realm.
It's like we've opened this door to a whole universe of possibilities.
Yeah.
As we wrap up our deep dive today, I think it's worth taking a moment to reflect on what we've learned. We started with these seemingly simple things like light and metal or particles acting like waves,
Right.
but they've really changed how we understand the universe and our place in it.
It is quite humbling to realize that the universe worked in ways that often don't make sense to us. But by embracing these strange ideas, we've made incredible technological advances and gained a much deeper appreciation for just how beautiful and complex the world is.
And the most important takeaway from our exploration today, the world is full of wonder and mystery and endless possibilities. By staying curious, by asking questions, and by embracing the unknown, we can continue to unlock those secrets of the universe, big and small.
So keep exploring, keep asking questions, and keep diving deep. You never know what amazing discoveries are out there waiting to be found.